Hello and welcome to this lecture on vector calculus. In this video, we are going to see about problem solving with Stokes theorem. So first of all, we see the statement. So here we used to relate the line integral with the surface integral. So the line integral f vector dot dr vector will be equivalent to the surface integral of gradient f cross f vector dot n cap ds. So quickly we go for the problem. Here is our f vector, and while doing a problem with Stokes theorem, definitely one of the surface will be kept open. If I'm giving cube, cuboid or parallelepiped, definitely that one of the surface should be open. If it is open, we can deal with only a Stokes theorem. If it is closed, we can go for Gauss divergence theorem. So clearly they have mentioned that S is the open surface of a rectangular parallelepiped formed by the planes. They have given the planes with this formation. There is a surface in the parallelepiped that will be a open surface which is lies above the XY plane. So here the boundary of the curve lies in the XY plane at x z equal to 0 will be on the direction of anti-clockwise from O, A, B, C again O. It will be on the anti-clockwise direction. So with this we get a graph, a parallelepiped. So the O, A, B, C, this will be a open surface. Okay, so x will be from 0 to 1. So we have to take the points x equal to 0, x equal to 1, y equal to 0, y equal to 2, z equal to 0, z equal to 3. With these points, we have plotted a parallelepiped graph. Then first we will evaluate the LHS part. In the given problem, they asked to verify the given function. So we have to solve both LHS and RHS. LHS part will be a line integral. So we will evaluate the line integral part. So first thing, we have to compute this line integral in the closed path OABCO. Okay, in that Z will be a 0. It will be a plane. So if you see the graph OA, so here x will be from 0 to 1. So x will be from 0 to 1. So I have said that it will be on the anti-clockwise direction. So 0 to 1. Then y and z are seems to be both are 0 in both points. If you see the point O, z will be, y will be 0 and z is also 0. Here y is 0, z is 0. So these 2 points are fixed points, but x will lie from 0 to 1. So that we are taking that fixed points on the line OA. Y is equal to 0, z equal to 0, and x lies from 0 to 1. Then what is the f vector they have given? Simply the given problem, f vector will be xy I vector minus 2yz j vector minus xz k vector. Okay, so just substitute these value, z equal to 0, y equal to 0, this becomes 0 and this becomes 0, this becomes 0. So whole the f vector will be 0. And what is a variable? X is a variable because it changes from 0 to 1. Other than x, y and z are kept constant because both at both points O and A we are getting 0. So x is the variable. So I am taking that dr represents dxi plus dyj plus dzk. If I find dy, it is also 0, dz is also 0, where dr vector will be dx I vector plus dy j vector plus dz k vector. So here from this equation we get dy 0, dz 0. So these both values are 0. Therefore we get only dx I vector. So we are writing that dr vector will be dx I vector. So finally in our LHS part will be like this. Over the curve C. Here the curve is OA. So f vector dot dr vector. Here it is 0. We have to integrate 0 with respect to a variable x, means definitely we will get 0. The next we go for the AB. Just see the AB. Here it is AB. See, x values are constant. Here it is 1, here it is 1. And see the value of y. Y is 0, here the y is 2. So y moves from 0 to 2. X is a fixed value 1, and see the value of z. Z is also 0. So we are taking that x is and z are fixed values. And if I find dx, it will be 0. Dz will be also 0. Here the variable is y. Y moves from 0 to 2. Y moves from 0 to 2. Okay, then take the given function. What's our given function? F vector, it will be xy I vector minus 2yz j vector minus xz k vector. Just substitute these values. X equal to 1, here it will be x equal to 1. Now y vector will be there, y I vector. Here if I substitute z equal to 0, this both values become 0. So this will be our f vector. That means y I vector. So y I vector. And what about dr? Here the variable is y. So I told you that dr vector will be dx I vector plus dy j vector plus dz k vector. So here the variable dy is a dy, and other than that x and y, x and z, we get 0. So dr vector will be dy j vector. Okay, so we write like this. And when we are going for this evaluation, we know that I vector dot j vector will be 0 with respect to dot product. If it having a same value, we will get 1. So I vector dot j I vector, it will be 1. J vector dot j vector, it will be 1. K vector dot k vector, it will be 1. Other than that, if I am getting any of combination like that, I j k, as like that, it returns a value 0. So clearly here it is I vector, here it is j vector. Definitely while multiplying a dot product, we get 0. So at the curve AB, we are getting 0. Now we go for AC. So here y and z will be a constant, x varies from 1 to 0. So we know that our f vector will be x y I vector minus 2y z vector z k vector minus x z k vector. If I substitute y equal to 2, it becomes 2x I vector. Then z, both the terms have a z value. So this will be the function. So 2x I vector. And dr, we know that dy will be 0 and dz becomes 0. So therefore dr vector will be dx I vector. Then along the curve BC, so here if I multiply I into I become 1. So 2x dx will be there. Then our limit x varies from 1 to 0. X varies from 1 to 0. Just see the graph. Here x varies from 1 to 0 in BC. So we are taking out the point 1 to 0. So if I equate this, 2 will be a constant, x 0 1, then it will be 2. While integrating this, it will be x square by 2. 2 will be cancelled, 0. So what you will get? 0 minus 1. So we get minus 1. And the next step, while we are going for CO, if you see the graph CO, here x is a fixed value, x equal to 0. Y varies from 2 to 0. Z is also fixed. Y varies from 2 to 0. Y varies from 2 to 0. Okay. 2 to 0. Other than that, x is also 0, z is also 0. So if you see the function, f vector will be xy I vector minus 2yz vector k vector minus xz k vector. If you substitute the value xz, x and z will be on all the three terms, so becomes 0. and here the variable will be y goes to 2 to 0. If I integrate 0 with respect to any of the variable, I will get 0 alone. So we have completed the full cycle. Therefore, while adding up all the values, I'm getting that LHS part as -1. Now we are going for the RHS part. So in RHS part, we want to evaluate the W integral over the surface with the cross gradient cross f vector, then dot n cap ds. This is the normal vector. So first we will evaluate this gradient cross f vector. So for that we have to list I vector, j vector, k vector, and here this represents dou by dou x, this represents dou by dou y. It will be of dou by dou z. And here you just see the function. What is the function we had? We have the function f vector as xy, I vector, 2y z vector minus xz k vector. So this we call it as f1, f2, f3. So thus here it is f1, f2, f3 without ijk, with here the entity ijk. So then we have to go for the calculation part. So what we will do, a usual matrix calculation, matrix determinant. So while going for the determinant, we have to fix the entity and that corresponding row and column. We will fix the values. So first I vector, then here if I fix this now, I will leave this column and this row. So here it will be dou by dou y. Thus here it will be minus xz and minus of, then again here dou by dou z of minus 2yz. Then I go for y. There I will put minus j. Here I will leave this column and this row. So remainingly dou by dou x of minus xz minus of, then I will take z, dou by dou z of xy. Then last k vector plus k vector into dou by dou x of minus 2yz minus of dou by dou y of xy. So while differentiating this, I will get the value 0. Here I will get minus 2y. So here minus and minus plus, so I am getting the 2y. Okay, in I vector, so I am having I vector. Then if you go for this, here it will be minus z. Here already minus is there, so minus j vector will be there. Here this becomes 0. And if I go for this value, there is no x term, this becomes 0. And here there is the y, so definitely minus x k vector, minus x k vector, we get this. And we are going to evaluate this RHS part. So for each of the face, first I will take the first surface, this will be S1. Okay, so if you see this, here we have 4 points, 0 to 2. So just see the value of x. X will be 0, here x will be 0, here x will be 0, x will be 0. So in all the places x will be 0. Okay, if you see other than that, y value move from 2 to 0 as same 2 to 0, y varies from 2 to 0. Okay, and if you see the z varies from, this is the z axis, so here we have z axis, so it moves from 0 to 3. So y moves from 0 to 2 and z moves from 0 to 3. So with this, here the first equation in the surface, I am fixing the equation x equal to 0. So the surface x equal to 0. So y moves from 0 to 2. Z moves from 0 to 3. So according to this, we are placing the, how this perpendicular line will be for the surface, it will be moved towards outside. So move towards outside, na, it just opposite to the x-axis. X-axis will correspond to I vector. It is opposite to this, na, here it will be minus I vector. So the normal vector is minus I vector. And what we have to do, we have to take the usual formula on the RHS part. Already we find the gradient cross f vector. Now we fix the n cap. So, and here according to with this, what the value we have to find the two of the variables out of three. So according to this, there will be dx dy dz correspondingly any of two. So with this, our gradient cross effector will be 2y. While substituting these values, x becomes 0, no? So our effector, the gradient effector is 2y z minus x. Here I have taken all this value, and if I substitute the n vector, here it will be I vector and I vector becomes 1. Other than that, everything will become as 0. So while multiplying this, n cap is minus I into this part, we are getting 2y minus 1. So finally minus 2y. Okay, now we are going for the double integral. So simply here y and z are variable, x remains a constant, x is a 0. So the limit of y will be 0 to 2, 0 to 2, limit of z will be 0 to 3. So we have to integrate this function with respect to y and z. By fixing these limits, we get finally minus 12. Okay, so how do we evaluate this? I will evaluate the inner integral first. So it becomes y square by 2, 0 to 2 dz. Then minus 2, 0 to 3. It becomes 4 by 2 minus 0. It will be definitely the same. Then dz will be there. So here it is 2. So minus 4 will be there. Then z 0, 3. So minus 4 into 3. I am getting minus 12. That's it. Okay. Next. This is the region. That means we see here, this is the S1 surface. For our simplicity and understanding purpose, I have given that it will be on x equal to 0. So here the plane will be YZ plane. So Z moves from 0 to 3, Y moves from 0 to 2. That's all. Then we go for the next surface. This we call it as S2 surface. Here you just see that x will be in all the 4 points, x will be equal to 1. 1, 1, 1, 1. So here x will be a constant. Then you just see the value of y. So this is the y axis. It moves from 0 to 2. So y moves from 0 to 2. And see the z. This is the z axis. It moves from 0 to 3. 0 to 3. So with this, y moves from 0 to 2, z to 3. And I have to find the normal vector. This is the face. This is the surface. Normal na perpendicular. It is along the x-axis. X-axis is denoted with I vector. So our normal vector will be I vector. Okay. So now already we have find gradient effector and n cap is I. The gradient effector will be 2y I plus zj minus xk. So if I multiply with I will get the 2y. I vector and I vector becomes 1. So 2y. Then we have to go for double integral. Here the variable will be y and z. So y limits will be 0 to y, 0 to 2, and z limits will be 0 to 3. And while integrating, I am getting 12. As same, this is the plane. This is the surface on yz plane when x is equal to 1. Then we go for the S3 surface. This will be the S3 surface. So if you see here, in all the places, y will be seems to 0, 0, 0, 0, 0. Then other than that, here x moves from 0 to 1, x moves from 0 to 1, and y moves, z moves from 0 to 3, z moves from 0 to 3. With this, I am taking out x moves 0 to 1, 0 to 3, and we have to find the normal vector. So this is our z axis, this is our x axis, this is our y axis. For this, we have to find the outward normal. Outward normal will be opposite to y. Y represents j vector. Here opposite side na, it will be minus j vector. So I am getting that minus j vector. So finally we have to multiply the n vector with the gradient effector. I am getting minus z. Then we have to go for the same procedure, double integral process, z dx dy with here 0 to 1, x value is 0 to 1, y value, z value is 0 to 3. The same integration process. So already there is minus z. So minus 0 to 3. I will evaluate this. Here z will be a constant, so we may take z. So while with respect to x, integration differentiation will get cancelled. 0 to 1 dz will be there. On the next step, 0 to 3 z with respect to x, we will substitute the limits. I'm getting that as minus z 0 to 3 dz, we get dz square by 2. Already minus is there. 0 to 3, I'm getting that minus 9 by 2. That's all. Okay, this is the xz plane when the equation y equal to 0. The third surface as same here, this will be the fourth surface. Okay, so if you see here, in all the values, what will be the common? Y equal to 2, y equal to 2, and you just see the z moves from 0 to 3, z moves from 0 to 3. Then what about x moves from 0 to 1. And what about the outward normal? This will be parallel to y represents j vector, so plus j vector. That's all. Then as usual, you just take the gradient f vector into the normal, then you will get z, because j vector will be a 1, and then go for the double integral, then you will get the value 9 by 2. Then at last this will be the graph on xz plane when y equal to 2. Then the next surface, the last surface, of course, totally this parallelepiped will have 6 surfaces. Then already they have omitted one of the surface, that will called OABC. This surface is omitted. Okay, so we won't consider this surface. Other than that, this will be the S5. Okay, so if you see here, in all the points, z will have 3, so this is the fixed value. Then you have to see for x moves from 0 to 1, 0 to 1. And if you see y, this is the y axis moves from 0 to 2, 0 to 2, 0 2. X moves from 0 1. So with this, what will be the normal vector? It will be outward like this, to the z axis. Z axis means k vector, so here it will be k vector. Then usual procedure, we multiply with that, I'm getting minus x. Then we will go for a double integration part. Then while x will be the limit from 0 to 1, y will be having the limit from 0 to 2, then finally I'm getting minus 1. Then this will be the graph. So while adding up all these values, okay, finally we get an RHS part. If I sum up all the surfaces, if I sum up all the surfaces, so here I'm getting minus 1. If you go for previously, here it will be 9 by 2, 9 by 2 minus 9 by 2 minus 9 by 2 plus 9 by 2 will be cancelled. Here it will be 12, here it is getting minus 12. So finally I'm getting 12 minus 12 plus 9 by 2 minus 9 by 2, at last minus 1. So everything get cancelled. Our RHS part is minus 1. So already we proved that LHS part is also minus 1, and now I'm getting RHS part is also minus 1. So LHS and RHS are equal. So hence the Stokes theorem is verified. Okay, so now we go for the exercise problem. Here I have given the same similar type of function f with this region x equal to 0, x equal to a, y equal to 0, y equal to b. It is also very similar and easy problem, so you can solve by yourself. And I'm giving the answer. The both LHS and RHS will be equal to minus 2ab square. Just try it by yourself.